Hello. In this video, we'll walk through the process of building an LNG storage tank model using the LUSAS Tank module and carrying out a design check step by step. Here's the overall workflow we'll be following. A 2D thermal analysis, extraction of the temperature distribution from the thermal results, a 2D beam stick seismic analysis, extraction of equivalent seismic loads for a 3D pseudostatic analysis, creation of a 3D shell model, application of thermal loads, application of equivalent seismic loads, definition of load combinations, and finally, the design check. In tank definition, we'll enter the parameters needed to build the model. In the modeler, go to tank greater than tank definition. Set the material type to concrete. Then select all three options: 2D axis emetric coupled thermal/structural, 2D beam stick, and 3D shell structural. By selecting all three, this tank definition can be reused across all three model types. For the input values, we'll keep the defaults already set in tank definition. For a detailed explanation of each parameter, please refer to the LNG tank user manual. Once you've finished, click OK to save the data to the modeler. You can check the tank definition you've just created under the Utilities tab. Next, we'll create the coupled thermal/structural analysis model. Go to Tank, create 2D model, coupled thermal structural. Select the tank definition data we defined earlier. Enter a model file name and click OK. Then click the Solve Now button at the top of the modeler to run the analysis. Once the analysis is complete, go to the Tree View, Analyses tab, and set the operating condition load case of the thermal analysis as active. We'll now extract the average temperature and linear temperature gradient through the wall thickness from the thermal results. These values will be used as the temperature load inputs for the 3D shell model later. Go to Tank, Excel Tools, Export Temperatures. If you need to consider both maximum and minimum ambient temperatures, update the ambient and ground temperature values accordingly, rerun the analysis, and extract the temperature distribution again for each case. The temperature distribution results will be saved as an Excel file in your working folder. Next, we'll create the 2D beam stick seismic analysis model. Go to Tank, create 2D model, seismic. Use the same tank definition we defined earlier. In the seismic analysis dialog, select the tank definition data and specify a model name. Set the design code to Eurocode and create both a horizontal model and a vertical model separately. Keep the default values for all inputs. The horizontal model consists of the outer tank, inner tank, soil springs, non-structural mass of the roof, and fluid mass. The convective and impulsive mass positions of the fluid are calculated according to the selected design code and saved as a spreadsheet in your working folder. Click OK to generate the model, then click Solve Now to run the analysis. In the Tree View Analyses tab, activate the CQC or SRSS combination result and then use the diagram tool to display the shear force diagram. The vertical model is set up by selecting the beam stick vertical option in the seismic load dialog. In this model, 4 joint elements share a single node. If you select ACI as the design code, the mass and joint for liquid rigid joint element will not be included. The maximum inertial forces and hydrodynamic effects obtained from the response spectrum analysis of the beam stick model are converted into equivalent static loads and applied to the 3D shell model as acceleration loads and structural loads. Now, we'll create the 3D shell model. Again, we'll use the tank definition data we defined earlier. Go to Tank, create 3D shell model. In the dialog, select the tank definition data and enter a model file name. Keep the default values for all remaining inputs. Click OK to generate the model. Next, we'll add thermal loads to the 3D shell model using the thermal analysis results. Go to Tank, add load in thermal. Specify the path where the temperature distribution result file is saved. Then click OK to apply the loads. You can confirm that the thermal load has been added under the loading section in the tree view, Attributes tab. Next, we'll add the equivalent seismic loads. Go to Tank, add load in seismic. In the dialog, set the design code to Eurocode. Then enter the acceleration and fluid loads for each member in both the horizontal and vertical directions. You can confirm that the seismic loads have been added under the loading section in the tree view, Attributes tab. Now, we'll define the reinforcement arrangement. Go to Tank, Design Checks, add / update rebar and tendons. In the dialog, click Download Template to save the rebar layout Excel template to your working folder. Open the file and define the reinforcement for the slab, wall and roof, along with the tendon layout for the wall and slab. Once done, specify the path where the file is saved to apply the reinforcement data to the model. Next, we'll define the load combinations. Go to Tank, Design Checks, Design Load Combinations. In the dialog, click the Download Template button to save the load combination template to your working folder. Define your load combinations in the template, then select the completed file in the dialog. Any load combinations that already exist in the model will not be deleted. However, if an existing load combination has the same name, its load factors will be updated. Any new load combinations will be added. You can confirm that the load combinations have been created in the Tree View Analyses tab. Now, we'll run the analysis and move on to the design check. Go to Tank, Design Checks, Enable. In the dialog, select the design code and define the required user inputs. Click OK to apply the design code. Set the load combination you want to check as active. Add a contour layer and review the util_pm values. Util_pm represents the utilization ratio for the hoop direction axial force and moment combination. A value of 1.0 or below indicates that the section satisfies the design code requirements. Now we'll generate the design check report. Go to Tank, Design Checks, Design Check Report. In the dialog, define the position by angle and specify the group to be checked. Select the items to include in the report, then choose the target load combinations or load cases. Select all three options, PM report, shear check report, and utilization summary report, and generate the report for all load combinations. The report will be saved to your working folder. In the PM report, each point on the PM interaction diagram represents the axial force and moment position for a given node under the design load combination. If all points fall within the PM interaction diagram, the section satisfies the design code. Any points falling outside indicate a util_pm greater than 1.0, which means additional reinforcement or an increase in section thickness is required. The shear check report summarizes the design check process and results for shear in each tank member. It presents the calculation of the concrete shear resistance and the basis for the utilization ratio relative to the applied shear force. The utilization summary report lists the utilization values calculated at each node for every tank member, covering the load combinations selected by the user. That completes our walkthrough of the analysis and design check process for an LNG storage tank using LUSAS. Thank you for watching.